Hello, we're going to talk about sequences. A sequence is something you're probably familiar with, but where we're going may be entirely new to you. But up here, basically a sequence is just a list of numbers, or a list of anything. But we're going to say it's a list of numbers that follow a logical pattern, and usually a sequence may be called out by a letter, subscript name, here A sub n. And this sequence is 1, 3, 5, 7, and it keeps going. A is the name of the sequence, and the n is used to index the terms. So A sub 1 is basically the first term in the sequence, which is 1. A sub 3 is the third term in the sequence, which happens to be 5. So that's very easy. But as you say, this sequence here follows a nice pattern. And sometimes it's a little bit easier to write how a sequence is created than listing all the terms. So here's a way that a sequence may be written in terms of an expression. This A sub n is 3 times the quantity of n plus 4. So when you plug 1 in for the first term, you'd have 5 times 3, which is 15. When you plug 2 in, you would have 6 times 3, which is 18, and so on. So this formula would let you jump to any term in the sequence. So if I wanted the 100th term, A sub 100, I could plug it in and it would be 104 times 3. So I don't have to look at the whole pattern. Okay? Sequences. So there is another type of sequence that can be kind of useful here. There we go. A recursive sequence. We won't use these very much, but it is good to talk about. A recursive sequence, probably the most famous that you may have heard of is like a Fibonacci sequence, where you add the previous 2 numbers to get the next number. Well, in this case, when we do a recursive sequence, we define the first term, which A sub 1 is 1, and then we define every term off of previous terms. So to get the next term, which would be A sub 2, here where n would be 1, so A sub 2, if we're saying 1 plus 1, would be whatever A sub 1 was plus 3. So that would be 1 plus 3, which would be 4. And then when we want the third term, we would add the second term, which was 4, to 3, and get 7. So in this way, it is very hard to jump ahead. So if I wanted the 100th term, either I'd have to define it differently, or I'd have to calculate the first 99 to get there. Okay. So here's a couple of sequences you could try. Let's just ask you to list the terms. If you want to pause and then try and work them out, the answers will be on the next slide. Boosh. Here's the answers. That last thing down here is 2500 if my head is covering it up. So once you understand what a sequence is, we're going to talk about infinite sequences, and we're going to talk about convergence and divergence. So basically right here, my second sentence, if the terms in a sequence approach a numeric value, which is a fixed specific numeric value, then we say the sequence converges to that value. We'll go through some examples of that in a moment. What that really is kind of like a limit, though. If we think about things getting close to a specific value, then that's a limit. If the terms do not get close to a specific number, then we say it diverges. Okay. And generally, if something does not get close to a specific value, usually one of 2 things happens. Either the terms bounce around, which means they kind of go up and down, kind of like a sine chart might, or excuse me, the sine function, or they might just go off to infinity, kind of like a rational function might get large. Okay. So let's do some examples here. So we're going to use the limit to talk about where a sequence goes and whether or not it converges or diverges. So the first one we've got here is 1 over n. So we want to figure out that if we wrote down all the terms in 1 over n continually, do they go to a specific place? Okay, so the first term would be 1, the second would be 1/2, then 1/3, 1/4 as we put in those indexes. But really what we're trying to do is see what happens if we continue that on forever. So if we let n go to infinity, 1 over a really big number would be 0. So this sequence converges to 0. So we use the limit to get that. Now the second example here is -1 to the n. So if we raise that to, if we take that limit as it approaches infinity, right here, then every time we go to the next index, we're increasing that exponent, and it goes between +1 and -1. So it just kind of bounces back and forth between the two numbers, -1 and +1. So it really doesn't approach any strict value. So we say that does not exist. The limit does not exist. So we would say it diverges. Okay, that sequence diverges because it does not go to a specific number. So whenever we're trying to figure out if a limit exists as we go to infinity, there's a couple things we have in our back pocket that we could use. Okay, some of these we'll do some examples with, and some of them we won't. But L'Hopital's rule, you may remember that if you are taking the limit of a rational function and you get infinity over infinity or 0 over 0, you can take the derivative of the numerator and denominator and try again. Rules for horizontal asymptotes. So when we have a polynomial over a polynomial, we kind of compare the exponents of those, the degrees. Sometimes we may end up rewriting an expression. We might be able to cancel something out and get something simpler. There's a sandwich theorem that is also helpful. This we can talk about. Okay. From the book, there are some nice limit definitions that we can use. So just keep these in mind and keep them handy. One thing I do have here, rule number 1. So sometimes we can kind of change these rules up. So the limit is n approaches infinity of the natural log of n over n equals 0. Basically the reason that happens is the natural log of a number usually makes it smaller. So we would be getting a smaller number on, well, the top would not be growing as fast as the bottom. We could also use L'Hopital's rule to show that. But if we flip that over, since the bottom is bigger than the top, we would say that thing goes to infinity, which would diverge. Okay, so whenever we have a rule, we can change that rule a little bit for different circumstances. Here are some practice problems. Number 1, you can actually use either L'Hopital's rule, or you can use the rational functions horizontal asymptote rule, degree of 5 on top, degree of 5 on the bottom. Number 2 here, this actually uses one of the rules from that previous slide. And number 3, the cosine, we'll see what happens there. So you can pause this and think about it, or you can go on. So as I said, the first one, you can use the rational function horizontal asymptote rule, which since your top exponent is 5, your bottom exponent is 5, you would get the coefficient, which is 3/4. The second one uses a rule number 5 from that list that I gave you, 7e to the n. So these first two converge because they go to these values. So if you were to use something like Excel or make a table or just calculate values, you would get quite a few of those, and you would see that they go to these values. The last one, cosine of n. So if you think about a cosine curve similar to a sine curve, it just kind of goes up and down, up and down. So it doesn't go to a fixed value, it just keeps cycling through different numbers. So the last one diverges. Okay, so we're talking about when a sequence converges, as we keep writing them out, they get closer and closer to a fixed value. And diverge, they do not, which means they bounce around, or they might go to positive or negative infinity.